water. And this proceeds via a carbocation intermediate. We know that this proceeds by a carbocation intermediate. And carbocation intermediates, we learned just now, are problematic because, let's just say they could be problematic. They can rearrange. If we want to make a very specific alcohol from a very specific alkene, this might be a problem for us if it rearranges to something different. So there's another method developed to do hydration of alkenes. This is method 1. Method 2 takes an alkene. We learned a little bit about it in our last lecture, overnight, our pre-lecture video. Step 1 will be to add mercury diacetate in water. And step 2, for this overall particular process, will be to add NaBH4, and we'll again hydrate an alkene in this 2-step process, and no rearrangement takes place. So you can see why I introduced a problem with carbocation intermediates today. They rearrange. Now we're actually going to explore a different set of conditions where rearrangement is impossible. And the good thing about this set of conditions, it has some striking similarities to bromonium ions, which we studied slowly, methodically yesterday. Our specific example today, we'll take methyl cyclohexene. We're going to take mercury diacetate, in water, and we're going to explore this first step, which is called oxymercuration. We're going to add mercury and oxygen across this double bond in the first step. So this first step is called oxymercuration. Mercury is kind of a funny metal. We almost never draw metals with covalent bonds to them. If this was sodium, we could never draw a covalent bond. It would be ionic. But sometimes, some metals, like transition metals in different locations of the periodic table, can do different things, and they can form semi-covalent bonds, and we can draw them like this. But when you take this particular compound and plop it in water, it actually ionizes or dissociates, and we make acetate plus mercury monoacetate. And this is what we actually get in water. Okay, that's the first part about water. Water is going to play another important role momentarily. So let's redraw our alkene. I'm going to flip it. I want to put the methyl group on top. And we're going to draw mercury next to it. And this is our electrophile. It's obvious it is because it has a plus charge on it. It's like adding a proton or adding Br2 where bromine is electronegative. So we now have an ionic salt. This becomes our electrophile. Our arrow pushing exercise starts from the alkene. It goes to mercury. And if this was H+, we'd be building up a carbocation at this tertiary position. But mercury is atomic number 80. It has lots of electrons, even though we don't draw them. Mercury is atomic number 80. It has lots of electrons, but we don't draw them. So in the slides or the notes, it actually had 2 electrons drawn here. That's kind of funny because that's not really the valence structure for mercury. But mercury has lots of electrons, and it's going to immediately bond back to the positive charge that's building up on this alkene. And if we actually draw this, what I've done here now, what I've drawn here is the logical result from these red arrows. Pi bond breaks, forms a new bond to mercury. Mercury bonds back to the other carbon, and we have a mercurium ion. It's very much like a bromonium ion. It's a three-membered ring. It's very reactive. At this stage, we have lots of water around. If this was bromonium ion, and we had lots of water around, the same thing would happen. Water attacks from the more substituted side of this mercurium ion, this three-membered ring. We're going to make a bond from the bottom. This methyl group is going to get pushed up. And these electrons are going to go back to mercury. Okay, so think about what this is going to mean and what we're going to draw. Think about what these two arrows mean and what we're going to draw. We're going to have H2O attached to the top carbon, the more substituted one. As a methyl group, this has a hydrogen. We're going to break this three-membered cyclopropane ring, or this mercurium ion ring. It's going to pop open. So we'll have four things attached to this carbon, four things attached here. Mercury is going to be up and attached here. Water will be down and attached to the back there. So I'm just going to try and creep the slide up just a little bit here so I can leave it here and keep referencing it. What we get next from these arrows, methyl group comes up, mercury comes up, hydrogen stays down. We have this particular type of intermediate, and we lose an acidic proton on water unless we do an acid-base reaction. Some of you might like using water to do it. Well, I like using acetate to do it. You can use whatever you want to do it, really. This is not the important point. Just an acid-base reaction here, pull off the acidic proton on the oxonium ion, and we get to our product of oxymercuration. Which has an alcohol at one position, mercury at the other position. And this is the result of oxymercuration or oxymercuration product. Key points: no rearrangement ever happens, and that the stereochemistry of the two things went on are trans. This group and this group are trans to one another, and that's the result of anti-addition. Mercury is up, the second thing comes in from the bottom. That's called anti-addition. There were better slides in the pre-lecture video that showed the side-on view I kept referencing in class yesterday. This is a result of anti-addition. We never have a three-membered ring here. The second group has to come in from the opposite side, and then the resulting stereochemistry in the product, which reflected that this was on top, this comes in from the bottom, and these are trans related to one another. The last step is a step you just have to memorize the reagents to do this. NaBH4 will it will do a process called demercurization or demercuration. Demercuration just seems removal of mercury. I'm not going to worry about the mechanism. Please don't ask me about it. You just have to memorize these conditions. If you ask me about this mechanism, I'm going to tell you to look it up in the textbook because I'm not going to spend our precious time on it. So if you're curious about it, I'm not going to stop you from it, but I'm never going to ask students to explain this mechanism. But definitely going to ask you to memorize that we remove mercury using sodium borohydride. The step is called demercuration. Probably mnemonically, you can develop some sort of rationale for looking at this molecule and then it has lots of hydrides attached to it. So we swap mercury, Hg, for H. And this final product is an alcohol. It's a result of hydration. We've added a hydrogen atom to one side, OH to the other, so it's hydration. And unlike reaction with acid and water, and that goes through carbocation intermediates, this never rearranges. Notice that the alcohol is at the more substituted position, just like we would expect for our normal sets of reactions. So this you have to put to good understanding how this mechanism works, particularly the steps in red, acid-base reaction, which we learned yesterday, trans stereochemistry, and then this final step. So this is a new reaction. We're going to move faster today. and it's going to build on the things that we did yesterday. So if you have a good foundation yesterday, all of this should feel not too terrible. First part, weird, but three-membered ring, not weird. Adding water to the more substituted opposite side, not weird. Pulling off an acidic proton, done that already. Showing that these have opposite stereochemistry. It's the same as if we did this reaction with bromine and water like we did yesterday. Final step, little different. So largely, it looks different at first glance, but if we look at it carefully, if we take a deep breath, this is something that you've already practiced and are trained to do yesterday in class. We're going to look at another example of anti-addition that results in trans products.